everyone, welcome back to the course on Introduction to Multi-Agent Systems. In today's lecture, we'll explore the spectral properties associated with non-negative matrices. We are particularly interested in characterizing the spectral properties of adjacency matrices. So let's get started. As I said, our primary objective in today's lecture is to present tools which will allow us to calculate the spectral radii of non-negative matrices. Okay. So, the spectral radii, let me quickly remind you, is the maximum modulus of all of the eigenvalues of a given matrix A. So, how is it important, the spectral radii? Now, it helps us in calculating whether a particular given consensus protocol is convergent or not. So, which is something we will talk about in the subsequent lectures. But in today's lectures, let us see how can we actually find out the bounds of the spectrum of a given matrix A. Okay, let's directly get started with the results. Let us consider a non-negative matrix A. Now, for some vector x which is greater than equal to 0 and is real valued, in other words, we can also write like this, which is greater than equal to 0, and some positive scalars R1 and R2. The following properties hold. The first property is when we multiply x with a given matrix, suppose the vector that we get, which is A into x, is equal to or is greater than R1 times x. So, what do we have here? We have the vector x, we operate it with the linear transformation or the non-negative matrix A, such that the output that we get is strictly greater than some positive number times x. Now, if we are able to find such a positive number R1 of x, then R1 is always less than or equal to the spectral radius of R. Similarly, if now A of x is less than equal to some positive number R2 times x, such that x here is strictly greater than 0, then R2 is strictly greater than equal to, not strictly, R2 is always greater than equal to the spectral radius of A. Now, So, when the non-negative matrix that's given to us is additionally irreducible, then if R1 of x is less than or equal to A times x, which is again less than or equal to R2 times x, and R1 of x is not equal to A of x, which is also not equal to R2 of x. And the x which is given to us is strictly greater than 0, then we have the strong property that R1 is always strictly less than the spectral radius of A, which is again strictly less than the spectral radius, which is strictly less than R2, meaning what we find here is that if all of these nice conditions that are given here hold, then we have actually found a neat bound of the spectral radius of A. So, now let us look at the proof of this result, which is also not very difficult. Okay. So, let us get started with the first part. So, to quickly remind you, it is given to us that A of x is greater than or equal to some R1 times x. Now, in order to do the proof, let us define a matrix, a new matrix A bar, which is equal to A divided by the scalar R1. Then from the given condition, what we have is, if A of x is greater than or equal to R1 of x, R1 times x, it implies that A bar is greater than or equal to x. Now, let us multiply the equation that we have with A bar in an iterative manner. What will we get? Let us see. We have, I missed an x here. It should be A bar x is greater than or equal to x. Now, what we have is, let us multiply A bar on both sides, sum A bar times x, which implies that the LHS is nothing but A bar square, and we know that A bar times x is greater than or equal to x, meaning we get this. In a similar manner, let us multiply A bar one more time. It gives us again this, which means A bar cube times x is greater than or equal to x again. If we keep on repeating this process, what we get is A bar, let's write it here itself. If we keep on repeating this process, we get A bar raised to the power k times x is also greater than or equal to x. Okay. Now, in order to proceed with the proof, let us make a small assumption. We now assume that the spectral radius of A bar is less than 0. This is an assumption that we make. Okay. Now, because of this assumption, what happens is that, so we talked about the powers of non-negative matrices in one of our previous lectures, which says that if the spectral radius of a matrix is less than 1, then let us write it. As we raise A bar to the power k, where k tends to infinity, we know that, so when we raise A bar to the power k, where k tends to infinity, the limiting value of this becomes equal to 0. What does this imply? This implies that limit k tends to infinity. So, here 0 is an n cross n matrix, and this is now equal to the 0 vector, but let us see. Let us call this equation 1 and let us call this equation 2. Combining equations 1 and 2, what do we get? We get that 0 is greater than equal to x. So, combining equations 1 and 2, we get that 0 is greater than equal to x. But what did we assume in the beginning? That x is greater than equal to 0, meaning here we arrive at a contradiction. Meaning our supposition or our assumption that the spectral radius of A bar is strictly less than 1 is actually not correct, which implies that the spectral radius of A bar must be greater than equal to 1. And what is the spectral radius of A bar in terms of A? It is simply equal to rho of A divided by R1, which is greater than equal to 1, which further implies that R1 is always less than or equal to rho of A, which completes the first part of the proof for the first part of the result. So, what we have gotten is actually a lower bound on the spectral radius of A. The second part of the result was about an upper bound on the spectral radius. So, again, how do we go about it? Let us start. Now, okay, let me first write the statement to quickly remind you or show you here. So, the second result says that if we can actually find a positive number R2 such that Ax is less than equal to R2. In that case, R2 becomes an upper bound of the spectral radius of A. So, now let us start with the proof of it. Okay. Now, we know from the Perron-Frobenius theorem that for the non-negative matrix A, which is given to us, there will always exist a W which is nothing but the left eigenvector which is now greater than equal to 0 such that W transpose A is equal to the spectral radius times W transpose. This is what the Perron-Frobenius theorem gives us. Okay. Now, what is given to us? It is given that Ax is actually greater than equal to some R2 times x. Now, let us left multiply W transpose on both sides. This implies, what's given is Ax is less than equal to R2. Okay. So, let us left multiply W transpose, which gives us this R2x. Now, the RHS simply can be rearranged as this, and we know that W transpose A, from here we know that it is equal to rho A times W transpose, meaning this becomes rho of A times W transpose into x, which is less than equal to R2 times W transpose x. Now, what do we know about W transpose x? Let us see. We know that W is greater than equal to 0, and we know that x is strictly greater than 0. This implies that whenever we do this operation of W transpose x, we get a scalar which is strictly greater than 0. Now, let us number these equations. Suppose here this is some 1 and this is 2. Now, we see that both of them are strictly greater than 0. So, what does this imply? From equation 2, we conclude that the spectral radius rho of A is less than equal to R2. Okay. So, this completes the proof for the second part of the statement. We now have an upper bound on the spectral radius, but notice that the upper and lower bounds that have been given in statements 1 and 2 are actually not strict. You see that these inequalities are not strict. So, the inequalities here and here are not strict. So, what we are interested in is in trying to see if we can actually make these inequalities strict, meaning getting stricter bounds on the spectral radius, which is what is covered in statement 3. Okay. So, we will not do the entire proof of statement 3, but we will just go about doing a brief proof of it, and the rest is for the students to try it out by themselves. Again, please remember that a detailed version of these proofs can actually be found in the lecture notes or in the book on lectures on network systems by Professor Francisco Bullo. Okay. Now, let us get back to the proof of the third statement. Okay. So, in the third statement, it says that we have the inequality R1x less than equal to A of x, which is less than equal to R2 of x, such that none of them are actually equal to each other. Further, it is also given that the matrix A is now irreducible. So, the irreducibility of the matrix A is important in the proof of this. So, let us see how it works. So, A is given to be irreducible. From the Perron-Frobenius theorem, we then know that there exists an eigenvalue which is a dominant eigenvalue, and corresponding to that we have eigenvectors both left and right which can now be strictly greater than 0, meaning let us say that the dominant eigenvalue associated with the dominant eigenvector associated with the dominant eigenvalue is greater than 0, meaning W, which is now the dominant eigenvector, corresponding to the eigenvalue rho of A. This is actually strictly greater than 0. So, how does this help us? Let us see. So, since W is an eigenvector, we have the condition W transpose A is equal to rho A times W transpose. Okay. Further, it is given that A of x is greater than equal to some R1 of x, such that A of x is also not equal to R1 of x. Okay. Notice that here it is given to us that x is strictly greater than 0. Now, let us left multiply W transpose on both sides. See, before that, let us notice one more thing. We know that Ax is greater than equal to R1 of x, and additionally Ax is not equal to R1 of x, meaning there exists at least one I belonging to 1 to n such that R1 times xi is actually strictly less than the ith component of this vector. So, it follows straightforwardly from this condition. Okay. Owing to this, now when we left multiply W transpose on both sides, what will we get? Let us see. So, let us just write something here. This implies that, and now let us left multiply W transpose R1x and W transpose Ax. Okay. We have two vectors here such that one of the components, at least one of the components of one vector here is strictly less than one of the components of the vector on the RHS, meaning when we multiply now W transpose on both sides of the equation, we get a strict inequality here. So, it is not so difficult to think about it. So, you can pause the video here and try it out for yourself that this actually holds true. Okay. What does this imply? It implies that, let us write it. We can rearrange the RHS a bit more. What is W transpose A? From the Perron-Frobenius theorem, which is equation 1 here, W transpose A is equal to W transpose X. Which implies that R1 times W transpose X is strictly less than rho A times W transpose X, which, and do we know whether W transpose x is greater than equal to 0 or greater than 0. See, since the matrix A is actually irreducible from the Perron-Frobenius theorem as given here, we know that, this should be W greater than 0. Please note this here should be W greater than 0. Okay. Now, because of that, we have here that W transpose A x is strictly greater than 0 on both the sides. So, this further implies that R1 is now strictly less than the spectral radius. Okay. So, this shows one part of the proof about the lower bound of the spectral radius. In a similar manner, we can extend the proof to calculate the upper bound of the spectral radius as well. Okay. Now, this is a very important result. It helps us to know precisely what could be the bounds of the spectral radius of a given matrix A. Okay. Now, we will look at some more interesting properties associated with non-negative matrices. Okay. This brings us to an end of this lecture. So, in the next lecture, we will talk about the spectral properties, some more aspects of the spectral properties that are associated with adjacency matrices. Thank you.